In this tutorial, we will summarize the main lines of the Landau-Zener-Stüeckelberg model to analyze crossing between electronic potential energy curves in chemical physics. However, the Landau-Zener relation is also used in many other applications in physics. In this application, the x-coordinate represents the geometry of the molecule. For instance, it may be the internuclear distance between two atoms in a diatomic molecule or ion. We consider the case where two electronic configurations, denoted Phi1 and Phi2, are sufficient in the energetic domain. For instance, Phi1 and Phi2 may be an ionic and a covalent configuration, such as Na plus Cl minus and NaCl respectively. The average electronic energy when the system is described by these configurations are drawn in dashed lines, in blue for Phi1 and in red for Phi2. These average energies are called the diabatic energies. They are the diagonal element of the matrix of the electronic Hamiltonian, HEL. This operator describes dynamics of the electron for a molecule which is frozen at a given geometry X. This operator corresponds to the full molecular Hamiltonian minus the kinetic energy operator of the nuclei. The coupling between the wave function associated to a single configuration, Phi1 or Phi2, is the off-diagonal element of the matrix of this operator. It is represented in green. In the Landau-Zener-Stüeckelberg model, the electronic diabatic energies are assumed to be linear around the crossing. The button alpha and beta allow us to modify the slopes of the potential energy curves, for instance, like this, and here. The coupling H12 is assumed to be independent of the coordinate, so independent of the geometry. The value of the coupling may be modified by the button H12. The effect of the coupling is obvious when one considers the adiabatic energies, which are drawn in full lines. These energies are the eigenvalue of the matrix of the electronic Hamiltonian. The matrix is represented here above the graph. The adiabatic energies are simply given by increasing order for each coordinate. For instance, the ground state, which is drawn in blue, is formed by all the lowest eigenvalues of the matrix. And the first excited state, in red, is formed by all the upper eigenvalues of the matrix for each coordinate. Far from the crossing, the diagonalization has very few effects. The diabatic and adiabatic energies are very close. The curves are nearly superposed. On the contrary, close to the coupling, to the crossing, the curves are very different, and the gap between the two adiabatic potential energy curves is equal to 2 times the coupling between the two diabatic states. If we now consider the eigenvector of the matrix of the electronic Hamiltonian, we see that the adiabatic eigenvector exchanges the main configuration from one side of the crossing to the other one. For instance, the ground state, Psi1, corresponds to phi1 on the left, but it corresponds to phi2 on the right. In the region of the crossing, the eigenvectors, so the adiabatic function, are mixing, or more precisely are linear combinations of the configuration. And in the two-state case, the linear combination may be expressed by a rotation matrix which is parametrized by an angle which is usually called the mixing angle. This angle, theta, is drawn in red in the middle part, and the angle is varying from 0 to pi over 2. When theta is equal to 0, C1 corresponds to phi1, and when theta is equal to pi over 2, then C1 corresponds to phi2. At the crossing, theta is equal to pi over 4, so the mixing of the configuration corresponds to a mixing with equal weights for the two configurations. Let's now examine what is the main coupling between the adiabatic electronic functions. It is denoted G12 on the figure, and it is equal to the overlap integral between the first adiabatic function and the first derivative of the second one with respect to the coordinate. So the value of the coupling depends on the rate of variation of the adiabatic function with the coordinate x, so with the geometry of the molecule. And the principal message that this CDF allows us to illustrate is that when the coupling is strong in a representation, it is weak in the other one. To illustrate this, we consider a situation where the coupling between the diabatic state is very high. So I choose the maximum value here for H12. Then, when the coupling between the diabatic states is high, the gap between the adiabatic states is very large. The mixing angle is varying very slowly with the coordinates, and the coupling G12, so the coupling between the adiabatic states, is small. On the contrary, if we decrease the coupling H12, we see that the gap between the adiabatic states becomes very small. The rate of variation of the mixing angle is very large, and the coupling between the adiabatic functions now is a peak which is very sharp and very high. We will observe the influence of the coupling between the electronic states on the dynamics of the nuclei. In this CDF, we find again the Landau-Zener model with the diabatic electronic potential energy curves in dashed lines and the adiabatic ones in full lines. We may modify the slope of one of the diabatic curves with the button beta, for instance, like this, and we may modify the coupling between the two diabatic functions with the button H12, like this. The dynamics of the nuclei in each electronic state is described by a wave packet. The square modulus gives the probability to observe a given value of the x-coordinate. In other words, gives the probability to have a given geometry for the molecule. The norm of the wave packet this gives the probability to be in a given electronic state adiabatic in the upper panel and diabatic in the lower panel. We will now illustrate three behaviors: an adiabatic behavior, a diabatic behavior, and an intermediate case for which the Landau-Zener formula will give the probability of being in each electronic state. The initial wave packet is prepared in a region far from the crossing. In this region, the adiabatic curves and the diabatic ones are nearly superposed. So we have only one blue wave packet. This corresponds to being far from the coupling, from the crossing, and in electronic configuration phi1. In an adiabatic situation, only one adiabatic state must be populated during dynamics, and it is the Born-Oppenheimer model. And then the non-adiabatic coupling G12 must be very weak. To obtain this result, we have to modify the value of the coupling H12 between the two diabatic states. When H12 increases, we see on the left that the gap between the two adiabatic states increases and the coupling G12 really decreases here. We have also to choose a very low velocity for the nuclei, so I decrease the value of the parameter K0. Dynamics begins with run. When the motion is slow, the electronic configuration can reorganize so that the system remains in the same adiabatic state. We have only a blue wave packet in the upper panel. The exchange of configuration is clear in the diabatic representation. The blue wave packet associated with configuration phi1 becomes a red wave packet which is associated with configuration phi2. After the crossing region, so after the passage through the coupling G12, we may stop dynamics with run again. So we see that in the adiabatic representation, there is no transition between the two states. The wave packet is always blue in the upper panel. In the diabatic representation, we have a transition between the two diabatic states. So this means that we have effectively a change in configuration. We go from phi1 to phi2. So in the final situation, the description of the wave packet gives the same information. The wave packet is in the adiabatic ground state, and this corresponds to configuration phi2. So it is in the same adiabatic state, but the configuration is changed. We get the same information, whatever the representation used, to describe the dynamics. Now we will consider the opposite situation with a large coupling G12 between the two adiabatic states. To obtain this situation, we have to decrease the value of the coupling H12 between the two diabatic states. When H12 decreases, one sees on the left that the gap between the two adiabatic states in full lines decreases, and we also see that the coupling G12 in gray increases and it becomes a very large and narrow peak. We have also to increase the velocity of the nuclei, so I increase the value of the parameter K0. Dynamics again begins with run. This time, the nuclei are so fast that the electrons have no time to adjust their configuration, and they remain in the initial configuration V1. We see that after the coupling region, in the adiabatic representation in the upper panel, the blue wave packet now is a red wave packet. This means that we have a transition from the ground adiabatic state here to the upper excited adiabatic state here. And this also means that the system remains in the initial configuration V1. In the diabatic representation in the lower panel, the wave packet remains a blue wave packet. This means that we go from this configuration to this configuration, and it is always the initial configuration V1. So we have a transition between the two adiabatic states, but we have no transition between the two diabatic states in this situation. Let's now examine an in-between situation. We choose a different value for the diabatic coupling H12. I take a value in the middle, like this, and I also modify the value of the nuclear velocity. I choose this value for K0. Run, begins dynamics. And now we see that in the coupling region, the wave packet splits into two components. One component, the blue wave packet, remains in the initial adiabatic state, while the red wave packet continues in the second adiabatic state. Dynamics seems different in the two representations, upper and lower panel. However, far from the coupling region, we will obtain the same information again. For instance, the probability to be at the end in configuration V2 is given by the norm of the blue adiabatic wave packet. It is the probability to remain in the initial adiabatic state. It is also given by the norm of the red diabatic wave packet in the lower panel. And we easily see that these wave packets, adiabatic blue or diabatic red, have the same area, so they give the same information. The probability to be in one of the other adiabatic states are given here above the figure, so they are the norm of the adiabatic wave packet. And the aim of the Landau-Zener formula is to estimate the probability to have a transition between the two adiabatic states. In this example, it is a probability to be in the adiabatic state 2, so it is this value. It may be compared with the value given by the Landau-Zener formula, which is written in black above the figure. And we may compare the analytical expression with the result obtained by the numerical simulation. So let us consider what is this expression of the Landau-Zener formula. It is an exponential function, and the parameters are the coupling H12 between the two diabatic states, here in the numerator. In the denominator, we have the nuclear velocity here and the modulus of the difference of the slope between the two diabatic potential energy curves. We see that when h12 is very small and the velocity is I, the exponential function is close to 1, so we have a large probability to have a transition between the two adiabatic states. This means that we have a diabatic behavior. We remain here in the same configuration. On the contrary, when the coupling increase and the velocity decrease, the exponential function is now close to 0, and we have a very low probability to have a transition, so it is the adiabatic behavior. We remain in the initial adiabatic state.